All right. Hi, Tony. We're live.
Okay, good. I was going to warn you. For some reason, my computer, which is on the 100 network,
Yeah.
it's like 10 or 15 minutes difference in time than my AT&T phone. Go figure.
Go figure. But we should be. If anyone is there online, please send a note so that I know that this is working. Congratulations, everyone, getting through your first exam. I will send out some summary statistics by tomorrow. You've probably noticed I did finish going over. Everyone has had their grade manually reviewed now. That I made a number of corrections. If there's still something that it seems like you should get some credit for, one of the examples, like if you put proportions instead of percentages, I will give some half credits for that. I went through, I may have missed some of those types of corrections. So, but overall it was pretty good. Most of the class got over 80%. A large proportion of you got over 80%, so it was overall pretty good. I have just posted a makeup exam, mostly because there are a few people who really struggled on the exam. It's available. It's going to be more like an assignment. I'll send out some instructions with it. Probably I'll send them during lab. But the way it'll work is it's like an assignment. You'll get 2 attempts at it. After the first one, you can see what ones you got wrong, and I will average. I'll take your final submission on the makeup and average that with what you got during the original exam. So if you did pretty well, you can't gain too much from it. But if you did a ways below what you think you should have done or what you could do with a little bit of extra time to prepare, then please go ahead and take the makeup exam. There were, on Thursday, Professor Rendina did a tutorial session where he reviewed the exam. I recommend tuning into it if you want to see the parts that you missed. He did review the whole exam. And I think I will go ahead and get through this lecture, and then afterwards I can take any questions about the exam or going forward if there are any other questions. So our topic today is sampling variability and the central limit theorem. And I'm going to take it really slowly today. This is a very conceptual class because this is central to everything else we're doing in the class. This is the basis for confidence intervals. We'll be doing several different kinds of confidence intervals, but they're all based on today's lecture. And also hypothesis testing. You'll be learning about the t-test, the z-test. Those tests are all based on sampling variability and the central limit theorem. So I think today is your chance to understand where all of those tests are coming from. And in a lot of classes, this gets kind of skipped by and we go straight into doing the t-tests and all this stuff, but I've kind of spread it out because I really want you to have an understanding of where these tests are coming from. Everything else that's relating to normal distribution is coming out of this central limit theorem. We're going to review the difference between a population and sample because that is key to sampling distributions, and talk about the central limit theorem as it relates to the samples. And then towards the end of the class, I'm going to talk about ways that we get samples and just distinguish between experimental and observational studies, prospective and retrospective observational studies. I don't spend too long on those because I think you get a fairly good coverage of them in your intro epi class. The sampling and central limit theorem you can get in chapter 4 of your textbook, and then this bit at the end on study types and ways of collecting data is from chapter 1. So population versus a sample. A population is every individual that we're interested in. And who that is depends on the purpose of the study. It could be every single person in a state. It could be every single person in the country or the world. But that is what we call the study population, and that is who we're interested in, and it's everyone who we're interested in. So it's very important when you're doing a statistical analysis or reading about a statistical analysis to understand who your study population is. And as you've learned before, the only case generally where we ever actually have data for the entire population is a census, and in other cases we take samples. So we use some sort of random selection mechanism to select some individuals out of this population. So from one population, you could have any number of different samples, and your samples are characterized by how you sampled them and how big the sample is. When we're dealing with continuous variables, we're going to do inference on the sample means, and that's an important thing to keep in mind. All of these tests that we do, the t-test, the z-test, the confidence intervals, they're about the mean. So they're not about individual properties, they're about group average properties, right? So when you take a sample of 75 people, what we're going to use for inference is the mean of whatever it is that we're measuring about them and the variability. And we're going to use that mean to try to say something about the population average. It's the population that we're interested in. And again, when we're doing confidence intervals, when we're doing hypothesis tests, it's about the average. And I'll tell you that that's something that I'm going to get at. You know by now that I like trying to ask some conceptual questions on the tests. And on your next test, there will be some questions to try to get at, do you understand that these procedures that we're going to learn in the next few classes are about the mean and not about the individuals? And I can assure you that probably a bunch of you will get them wrong, because, well, hopefully not, because I've learned from past classes, and I'm really going to emphasize that conceptual difference, that it's about the mean, not the individual. This was an example, a data set from the book. It's a data from a big running race, 16,924 runners that participated in this 10-mile cherry blossom run in DC in I don't know, I think 2012, not 2009. Not sure, one of those years. So there's an interesting question. If we're going to do some analysis with this data set, do you think that those 17,000 runners, would that be a population or a sample? What's that? Yeah, I mean, it could be either, really. It depends on how you define your study population. If you, in the book, they say, you know, this is a population. We have the complete data for every single one of these runners. So as long as our study population is these 16,000 runners from this year, then it's a population. If our study population was going to be all people who do 10-mile runs, then it might be a sample. It would be a big sample. But for the purposes of today's class, and as they treat it in the book, this is a population. So that's a complete data set. And of course, only the organizers of the race are going to have access to all 16,924 participants. So you could imagine that if you were, you were someone from the press or somehow elsewise doing a study and you didn't have access to everyone, maybe you would just take some sample of them and try to time them and do your study using some subset of these. And then the point of the inferential procedures that will be used is that you could take really some small proportion of them, maybe only 30 individuals out of those 17,000, and actually say something well-informed from quite a small sample from that population. Yes, question? Good question. How do you know what is a good sample size? Yeah. So the most unintuitive part of that answer possibly is that it doesn't depend on the size of the population. It doesn't matter if you have 15,000 runners or if you have 5 million runners. What it does depend on is statistical power, which is something that we'll get into a little bit later. More questions about this? Something else? Right. There's a formula that you can use to tell you what sample size you need, and that's a power calculation. But one thing that is not in that formula is the size of the population. That's right. And what it does depend on is essentially how accurate an answer you want, what the natural variability in the population is, and how accurate a distinction between two groups you want to be able to make. Other question? Let's see, I'm going to correct this right now. This was 16924, and I think it is 2009. So we're going to treat this as a population. That's a lot of people. That would be an unnecessarily large sample for most purposes. If we take a random sample of 100 individuals from that run, and I'm plotting on the left here the running time for all 17,000 individuals, I'm plotting on the right the running times for a random sample of 100 individuals. Now my question for you, so this is a sample, this is one sample. Are the observations in this sample, are they an approximation? What are they an approximation of? I'll get back to it. Just think about that. Does it look like kind of like the histogram on the left? It does look kind of like the histogram on the left. I mean, the middle is at about 100, just under 100 for both. You know, it varies from about 40 to 140 in both. It's not, you know, it's not exactly the same, but it's pretty similar. And you know, that's what we would expect to see. If it's a random sample, we would hope that you know, there's some variability in this sample, but it's representative of the population, right? So some some notation, and I've told you this before, but just to remind you that we use Greek letters for things about the population. So the mean and standard deviation from a population are mu and sigma. And from a sample, these are statistics. So for the population, those are parameters. From the sample, they're statistics. And we use the regular English letters for sample statistics. So the mean and standard deviation are X bar and S. So the difference here is that mu and sigma would be calculated from all 16,900 individuals, and they're exact. You get that? They're exact. There isn't uncertainty in that because we have all of the data there. So that's just an exact calculation of the population mean and standard deviation. From that sample of 100, we can estimate a mean and standard deviation, and those are not exact. They're estimated from an incomplete sample. So population distribution, I think you should be comfortable with that by now. You know, we've had examples of population distributions, of distribution of test scores, distribution of blood lead levels. What other examples have we had of population distributions? President's age, right? Things that are based on the entire population. So what then is a sampling distribution? Sampling distribution, and this is going to take a while to sink in, it's not just the distribution that we get from a sample. What we do is we take a sample, we calculate some statistics such as the mean. A lot of what we'll be doing is with the mean, and then you repeat it. So you'll get a bunch of different means. Every time you take a sample, you calculate the mean. And that distribution of the means is your sampling distribution. Yes? Mm-hmm. No, it would be a sample of all samples of 10-mile runners. But it would be, so here is one sample of 100. We take this sample, we calculate the mean, we find that it's maybe 92, and then we take another sample independently, like randomly again, select 100 runners, calculate the mean. When we've done that twice, that's 2 points along, that's 2 measurements from the sampling distribution. The key point is that the sampling distribution here is about the means. It's not about individuals. Sorry, the second. Yep. Yep. Right. So as you do another sample, is it possible that some of the same people are in both samples? The answer is yes, it's possible. For everything in normal statistics, we will actually be only taking one sample, so that's not an issue. But for the sampling distribution, we will be assuming that the population is much larger than the sample, so that any overlap that you have is negligible. There are different statistical methods for small populations. If you have a population of 200 and a sample of 100, that is going to affect your sampling distribution. But everything that we learn will be assuming a large population. At least the population is large compared to the size of your sample, so that any overlap that you would get in 2 samples is negligible. Good question. Yes?
When you said about sampling distribution,
You said it's about the mean and not about the...
Right. Sampling distributions are about the mean. They can be about other things as well, as long as it's a continuous variable and we're doing the z-test and the t-test, it'll be about the mean. But the point is that the sampling distribution is about group properties, not individual properties. Which is good because we're in population health, right? So there are, you'll see it makes a big difference. The sampling distribution in general is very different from the population distribution. So it's important to remember that it's not a property of any individual, that sampling distribution. It's only a property of groups of individuals. Does that answer your question? So again, for the sampling distribution, the process is to take of that sample, the mean in particular, and then repeat. And if you repeat that over and over and over, what you will get is your sampling distribution. And anytime you have a sample greater than size 1, its variability, the variability of the sampling distribution is going to be less than the variability of the population. Anytime you take samples of greater than n equals 1, the variability in the mean of those samples will be less than the variability of individuals. Yep. Sample mean. That makes sense, right? Think of something like weight. Weight has a pretty big distribution in the population. Some people weigh much more than others. But if you were to go out and randomly select groups of 10 people, put all 10 of them on a scale and divide by 10, that variability is going to be quite a bit less than the individual variability. Because you're going to get some big people, you're going to get some small people, but on average it's going to be like your average person. So that's the really key thing that there are a couple key things about the central limit theorem, which I'm about to get to, but one of them is that the variability of the group is less than the variability of the individual. And here's an example. Serum cholesterol of individuals varying between about 75 and 350, but variability of the mean of groups of individuals is quite a bit less. This is for samples of size 25. So they have the same center on about 211, but the group variability is much smaller. Everyone comfortable with that? So what about in our runner's case? Here is that example again with the whole population. You can see that the largest frequencies, so that's the number of runners in one of these bins, is over 4,000. It's lots of people. And here's a random sample of 100 runners. So now here's a question for you. Is what you see here, is it an approximation of the population distribution or the sampling distribution? Keeping in mind that this is a sample. It's one sample. Who thinks it's an approximation of the population distribution? Okay, I see a few hands. Who thinks it's an approximation of a sampling distribution? All right, we have a slight majority in favor of the population distribution, and that's correct. It's an approximation of the population distribution because these are individuals. Each of the times being counted here is the time of an individual, and that's why it's an approximation of the population. If this were a sampling distribution, then each point in here would be an average of some number of runners. Now I'm going to show you some sampling distributions. So all of this you see here for 100 runners, this would be just 1 point on the sampling distribution, and it would just be this mean. So a mean of 35 minutes, that would be 1 point on your sampling distribution, whereas we have here 100 data points out of the population distribution. Any questions? Okay. However, before I show you some sampling distributions from this example, I'm going to tell you about the central limit theorem. There are 3 main parts to it that you'll have to know, and what it does is it relates the population distribution to a sampling distribution. And the first part of it is that the mean of those 2 distributions are identical. So if you have, in this example of the serum cholesterol, the mean of individuals in the population and the mean of the means of samples of 25 are the same. And that makes sense, right? You wouldn't expect, just because you're averaging some people together, to end up with a different average than in the population. So the means are identical. Now the second part, which you're going to get very familiar with, relates the variability, the standard deviation of these 2 distributions. And it tells you that the standard deviation of the population is related to the standard deviation of the sampling distribution, that is, or of the sample means, by this formula. And I write SE here because we're going to call this the standard error of the mean. So this is when we're taking means of samples of size n, then those means form the sampling distribution, and the standard deviation of that sampling distribution is this standard error, SE. And they're related by this factor of the square root of n. So this formalizes that thing that I said before, that as long as you have samples of more than 1 person, the variability of your sample means will be less than it was of individuals. Yes?
The standard deviation of the population related to the standard deviation
of the sample means, or of the sampling, or of the sampling distribution of the means. So remember, the population distribution is made up of individuals, the sampling distribution is made up of sample means. And that standard error, or standard deviation of the sampling distribution is equal to the standard deviation of the population over the square root of n. That's part 2 of the central limit theorem. So what else does this tell you about the effect of sample size? If you go from a sample size of 9 to a sample size of 25, what does that do to your variability of the sampling distribution? It gets smaller. And yeah, it gets smaller by a factor of square root of 25 over square root of 9. Yes? Yeah, the standard error is your uncertainty in your measurement of the population mean. So there are different ways you can think about it. The way I'm introducing it here is it's the standard deviation of the sample means. So if you were to take 1,000,000 different samples and calculate this, and 1,000,000 different samples of, say, size n equal to 25, calculate the mean of all of them, and the standard deviation, that would be your standard error. And that's one interpretation. And another interpretation, which is the, I guess the way we'll be using it when we get into confidence intervals, is that it's, if we only have one measurement of the sample, we have one measurement of a sample, and that's our best estimate of the population mean. It tells us the uncertainty, like the variability around that point estimate in our best guess at the population mean. And that's the interpretation that we'll use for confidence intervals. And the final part of the central limit theorem is that for large n, the shape of the sampling distribution becomes normal. Doesn't matter about the population distribution. So on the left, here's an example of a uniform distribution in the population. So if you take samples of n equal to 1, you have a uniform distribution between the minimum and maximum. But if you take samples of size n equal to 4, calculate the mean of each of those samples, and plot all of those means, it starts looking mounded up towards the middle. Like you're not likely to get all 4 of your random individuals down near the negative extreme or near the positive extreme. Go up to n equals 7, it gets a little bit more concentrated to the center, and n equals 10, more concentrated to the center and more normally distributed. On the right here, just some funky examples. This is a made-up, super wonky population distribution. Say this is something like, I don't know, something like weights, where you have only kindergartners and WWF wrestlers or something. So it's, you know, and I don't know, maybe men's and women's division or something like that. So you have, you know, a really wonky distribution in the population. But as long as you take random samples from that, random samples with increasing size, their averages become more and more normal. So I'm not sure what the sample size is here, but for a large enough sample, your sample means are normally distributed. You'll learn rules like you know, if n is greater than 30, then you can use the normal approximation. And that's fine, but it does depend on how wonky your original distribution is. The wonkier it is, the larger a sample you need for the sampling means to be normal. So put all together, it means that for a random sample of size n from a population with a known mean mu and a standard deviation sigma, then we know what the sampling distribution of means will be. It'll have the same mean mu, and it'll have a standard deviation that we call the standard error, which is sigma over square root of n. And we call it standard error just so it doesn't get mixed up with the standard deviation, which usually has to do with individuals. The standard error, remember, it's not the variability of individuals, it's the variability of groups. Some more examples of whatever your population distribution is. The larger your samples get, the more they all look the same. So individuality is lost in large groups, is what this means. So yes, how large is large for the central limit theorem to apply? N equals 30 is a pretty good rule of thumb. Although if your population is fairly normally distributed to begin with, you don't even need that much. But by the time you get up to n equals 30, almost everything will produce a normal sampling distribution. And of course, if your population is normally distributed, like blood pressures, like the test scores, then you don't need that minimum sample size, right? A sample of any size will give you normal distribution in your sampling means. So I got into this a little bit already, but again, that standard error tells us how much samples, random samples, will vary just by chance. So taking a sample of 25 or 50 or 100 individuals, you'll get a different mean each time, and that sampling distribution tells you how much those means will vary from one sample to another. All right, and back to that runners 10-mile data set. Here are a few histograms. This was of all 16,924 runners. Now in each of these, I took a random sample of the specified size and did that 1,000 times. So you're seeing 1,000 samples in each of these histograms. This, of course, is something you could only ever do in a computer with a simulation. When you go out and do a study, you're just going to have one sample. But it's important to remember, and I think this is actually a pretty, I don't know, people forget this in the like midst of data analysis or the midst of reading a paper about this sample that maybe was a very difficult sample, a very important sample. You know, it might have been a nationwide sample, it might have been thousands of people. To remember that that's just one point out of the sampling distribution that you're getting to see. And it's part of an entire distribution of samples that you might have gotten. And so what I'm doing here is actually repeating that experiment over and over. So you can see that every time you do your study, you get a different result just because of chance. So if each one of your studies has a sample size of 1, it's going to have a lot of variability. It's going to look like the population, that variability. And it has the same skew, has the same, more or less, range, everything. Going up to n equals 10, you see it's getting narrower, it's getting more normal, up to sizes n equals 25. So again, what I'm doing here is taking a random sample of 25 runners, calculating their average, these are ages here, calculating their average age, and plotting each one of those averages of 25 runners in this histogram. So this histogram represents 1,000 observational studies, each study having 25 individuals in it. Yes? No. No, so what this means is that I draw 25 individuals randomly from the population. I calculate their mean age, and I plot that, and then I repeat that 1,000 times. I know it was 1,000 times because I wrote a program that did this. I did replicate 1,000 times, take a sample of 25, calculate the mean, and it gave me then a list of 1,000 means from each of those n equals 25 samples. Yeah, so this is an in silico experiment where I'm able to repeat a study, and you can imagine. So it doesn't matter that this is runners. You're going to read papers where they will tell you what the mean age of their participants was, and they'll give you a confidence interval around that. That's based on this sampling distribution. It's based on the assumption that your sampling distribution is normal, and that you can estimate the standard error of it from this square root of n formula. And of course, the larger your samples get, up to n equals 100 each, n equals 1,000 each, the less and less variable the sampling distribution becomes. So if you're using a sample to estimate the population mean, you're going to have, the larger your sample, the less uncertainty you're going to have in the population mean. Yes?
You're just using n over and over again.
Mm-hmm.
So, I mean, I know here that it's variability, that it's n of means.
We always use n to mean the sample size.
Okay, so no matter whether it's the original n, which is, n of 25 each sample, because when you say sample means n equals 1,000, you're saying that you did n equals 25 1,000 times.
Right, so I shouldn't use n to say 1,000 there. That's like 1,000 replicates of the experiment.
Right, that's what I meant.
So, okay. But yeah, no. So this is the only time you're going to see a study replicated 1,000 times. Normally, there's only one replicate of the study, and n refers to the number of individuals in that sample. So let's call this k or something. K equals 1,000.
So in the formula for SE,
Mhm.
that n that's there, is that the n of your original sample size, or is that the n of?
That's the number of individuals in your sample. That's your
Oh,
sample
so that's
size.
That's your actual sample.
Yeah. So I'm using, this is the way you're going to see n used. It's,
Okay.
n equals 1 means that your sample is just one individual. N equals 10, it's 10 individuals. 1,000 has nothing to do with it. If I were to increase this to 10,000, this would look basically the same. I just chose 1,000 because it was large enough to produce a nice smooth histogram, but
But n is not, in this chart, n is not the individual, n is the number of times you've taken the sample.
no, it's the number of individuals in one sample.
So how are you getting all of that data from n equals 1?
Because I considered a sample to be one, I drew one individual, and whatever value, whatever age that individual was, that's the mean. So here I drew one individual 1,000 times, here I drew 10 individuals 1,000 times. Question?
Yeah, you said the larger the sample size, the less certainty or variability there is in the population.
The less uncertainty there is in our estimate of the population mean. Population mean is what it is, but we don't know what it is.
And is that the same thing as saying the less variability or uncertainty there is in the sampling mean?
Right. So for large N, there's less variability in the sampling mean, which means that if we repeat our experiment, we'll get answers more close to what we got the last time. There will be less random variability in the mean if we do multiple samples. Right. So we take one sample, whatever that mean is, that's our best estimate of the population mean. But we know from the central limit theorem what the variability in that sample mean is, just from random sampling error. And that tells us how confident we can be in using that estimate for the population mean. If n equals 10, we're less confident. If n equals 1,000, we're more confident. Yep.
So the minimum variability, you represented that. As you go further down, you have a thin peak, so you see less and less variability.
Yeah.
More variable. It will just come out more, so it'll be more.
Yeah, like this, right? So yeah, the fewer the number of individuals in each sample, then the more variability there is in the mean of the sample. So the key thing is if you don't have much funds or much time for a study, so you just pick 10 people, you're going to have, and you take this estimate of 32 years of age as the population mean, there's going to be more variability in that estimate than if we take a larger number of individuals for our sample. So, this is kind of confusing because you're seeing 1,000 samples here, whereas what we deal with in the real world is always one sample. But the key conceptual thing is to remember that you have just one sample out of an entire distribution of possible samples that you might have gotten. That one sample, that's not the population, it's not the truth, it's just a random sample. And as such, there's random variability. And the smaller your sample is, the more the random variability in your sample is. In your sample mean, or we will do other things. It could be your sample proportion. Any more questions? All right. Here's just one more review. I think we've done lots of discussing about this already, but these are actually, oh, sorry, this is for a proportion. So everything I've been telling you about is for a continuous variable. However, we can also write down the sampling distribution of a proportion. So this is for a binary variable, such as whether an individual has cancer or not, diabetic or not. When we take a random sample from the population and ask what proportion are positive or negative, or whatever, male, female, whatever variable we're looking at, there is sampling variability in that proportion, and it's based on the normal approximation to the binomial distribution, which we covered. And similarly to the central limit theorem, the sampling, as long as we have a large enough sample size, then that sampling distribution of proportions, so you take, if it's about prevalence, and this is a common thing you'll see in epidemiological studies, where there's a sample taken from the population and they want to estimate what's the prevalence of something, of alcohol use, whatever. You'll get a point estimate and a standard error on that prevalence, and that is based on this normal approximation for the sampling distribution of proportions. So if we were to repeat our study, we would find that the proportions that we get across all of the studies are normally distributed. They're centered on the population proportion P. So it sounds a lot like the central limit theorem, right? And it has this standard error with the proportion times 1 minus P times 1 minus P over N square root. Yes? Yes. Yeah, the population prevalence. So I would usually use prevalence to refer to the population, and use a proportion to refer to the sample. But prevalence is a proportion. Yeah, people don't use the word prevalence to refer to the sample, but conceptually, yes. Prevalence is the proportion in the population. Like if you're talking about alcohol use, prevalence would be the proportion of the population that use alcohol. And in your sample, your proportion would be, the number of people who use alcohol divided by the size of your sample. So you can use this, you'll use this in the same way if you have proportions, as long as you meet the large sample criteria approximations that we set for proportions. So this forms the basis for t-tests, analysis of variance, confidence intervals. A lot of the rest of what we're going to do in this course are based on the central limit theorem and on sampling distributions. Even we'll cover the chi-squared test. Basically, every hypothesis test in statistics is based on a sampling distribution. So it is really important to understand what a sampling distribution is, because if you do a hypothesis test, chi-squared test, there are tons of them. SPSS will let you click a button and do all sorts of them, and they're all based on some sampling distribution or other. And as I mentioned before, I just want to say this again, the size of the sample matters, but the size of the population doesn't matter. Remember that the standard error of your sampling distribution was the standard deviation in the population divided by the square root of n. So it depends on the individual variability in the population and on the sample size. What matters is that you have a representative sample. So how do we get samples? There are a variety of strategies, but here's just a bit of terminology for you. The study units or the sampling units, these are the individuals who make up the samples, so they'll often be people. The target population is all of the people who we want to study, which again could be all the people in a state, it could be only females, it could be only teenagers, it could be any number of things, but it's the population of interest. That's the ideal population, and then the study population is who we're actually sampling. So, and if there's a difference between those, that can happen due to selection bias. It means that your study population, you're not actually equally sampling from the target population, or you're in some cases you will intentionally sample in a non-representative way from your target population, but as long as you know that you're doing that, it's not selection bias. It's selection bias if the probabilities that you think you're sampling every individual with are not the probability that you're actually sampling them with. So if you do a phone survey and you assume that you're equally sampling every individual in the city, but in fact you're only sampling people who like to answer when they don't recognize the caller ID, then that's a selection bias. And the sampling frame is your list of all of the elements in the population that you use to select your sample. So in the running race, I started with an index of 1 to 16,900 that were the indices or the numbers of all of the runners, and that was my sampling frame. It's something that I could use to randomly select from. If you don't know, if you don't have some kind of a list of your population, then you don't know if you're randomly sampling from them. So here would be an example of selection bias where we've got a general population, and in this general population there's a lot of slightly nervous people. But if we take a sample from people seeking life coaching or something like that, you might get very non-nervous people and extremely nervous people. They have different reasons for seeking out the coaching. The point being that this is not a random sample of the general population. So the ideas, the concepts behind sampling distributions and sampling variation, they're the same whether we're studying observational or experimental data. Experimental data are where there's some kind of an intervention, where the people doing the study actually do the thing that they're studying. So they assign people to a treatment or a control group, or they somehow assign people to two different alternatives where they then can look for a difference in average behavior in those two groups. So the key thing is that there must be an intervention for it to be an experiment. It might sound like an experiment if something is like a clinical trial where all of the people who come through the doors of a clinic are given a questionnaire and stuff. It may sound scientific, but if there isn't an intervention, then it's not an experiment. And by the way, I'm sure you've heard this already in EPI if you've taken that already, but experimental studies are really the only way to prove causality. You might be able to suggest causality from an observational study, but it's impossible to rule out other unknown factors without doing an experiment. Among observational studies, here are a few of the main categories. There are cross-sectional studies. So that would be where you, at one given moment in time, take a sample from your population. So it's like a snapshot in time that observes just some cross-section of your population. The New York City Health and Nutrition Examination Study, which some of you will analyze data from later in the semester. That's a cross-sectional study because it's done every year, and it's a cross-section of New Yorkers that are taken to do this study. Retrospective studies are ones where we're already aware of something that's happened in the past. So an example would be the case control study with cancer patients and controls who do not have cancer. So we have taken people where we know some health outcome of them, and then we look into their past to try to predict what may have caused that health outcome. It's retrospective because we take them at the moment in time where we know it happened and look into the past to try and understand why it happened. And then prospective, which is, I think, the most difficult of all of them, is where you take a cohort of individuals, such as the Nurses' Health Study, which is out of the Harvard School of Public Health, where it was a group of nurses. If we were to say that all of you, the biostat PH750 students of Spring 2015 are a cohort, and recruit you to answer questionnaires for 15 years into the future, that would be a prospective study. So they're long, they're difficult to do, they require a lot of commitment on the part of the subject, and for any given health outcome, there'll generally not be very many of them if it's a low prevalence health outcome. And none of these can prove causality, but they can be very important in identifying potential reasons for health outcomes. So just to wrap up, hopefully by now you know what a sampling distribution is and how it relates to the population distribution. We covered sampling distributions of the mean, and that's what we're going to be focusing on. And that's related to the population distribution by the central limit theorem. And we covered experimental and observational studies. And I'm ending pretty well right on time. Are there any questions before I send you all down to lab? All right. I'll make an announcement in a little while about the makeup test and test that you've already finished. Thanks.